Hello everyone and welcome to my talk about functional programming in F#. If you come here with no experience in either of those things, that's great. I will teach you the basics, and hopefully after this talk you can get started writing your own F# programs or applying what you've learned to your C# programs. I'm going to assume you are a C# developer because a lot of the examples will be in C#. I'll teach you the building blocks of functional programming in C#, and then that will translate really well to how we do things in F#. I like functional programming because when I first learned functional programming, it gave me a new perspective on other things that I already knew about object-oriented programming and design patterns there, and very kind of simple basics of what it's like to write code and to write programs. The functional programming model, mental model, is much simpler for me to grasp, and for me it leads to less over-engineered code, and I can really deal with the essence of what I feel like I should be doing in a program. Its simple abstractions are powerful enough to do all of the things that I could do in an object-oriented program, but a simpler mental model allows me to think about my programs more clearly, and it makes it easier for me to write and read programs in general. I like to do it in F# because F# is really made for functional programming. If you do it in a language like C#, you can get a long way, but F# makes it a lot easier. F# especially has also really strong type systems, so you can encode things in types that you can't in C#, which leads to less unit tests and more, easier to use APIs. It's easier to use them correctly because you can make sure that the type system prevents you from doing something stupid or something that you're not allowed to do. And so finally, for me, writing F# programs is about joy in programming. It's much more pleasant for me to write stuff in F# or to, deal with other people's code in F#, especially when it's written in its functional style. If you don't know F#, F# is a general purpose language like C#, Java, JavaScript, TypeScript. You can write front ends in them, back ends in them, APIs, user interfaces. You can do data science. You can do everything. It's functional first, which means that you can do object-oriented programming, but it's especially made to do functional programming. It's on the .NET platform, which means there's a lot of interop with other languages. So you can, for example, write a library in F# and call it from your C# program, or the other way around. When you're writing F#, you're consuming the same, libraries and core functions and data structures that are in the .NET platform that you use from C#. Sometimes you'll be dealing with wrappers to make it more functional or easier to consume in F#, but you're in the same ecosystem essentially. F# has a very strong type system as well, like I mentioned before, and very strong type inference. So you can annotate your types, your functions or your variables with types, but you can often leave them out as well. So when you don't want to see all that clutter, you can leave it out, and it kind of is syntactically more pleasing and sometimes easier to read. The ecosystem in itself is also, a lot of goodies. Goodies like Fable is a JavaScript compiler, so it takes F# code and outputs JavaScript code. So you can write F# for the web, or even if you wanted to for Node.js. What I really enjoy with that is, for example, writing my web apps in F# using React, so I can combine the powerful type system of F#, leading to a lot less bugs, and writing my UI in React, which I also very much enjoy. And that combination is extremely powerful. There's a lot of model view update libraries, which is the Elm style of writing user interfaces. So you have Elmish and Avalonia, and there's a couple others. So this is a very popular pattern in the F# ecosystem. And F# also has something called type providers, for example, where you can take external resources like a database and have them represented as types while you're programming. So it works for database, it works for JSON, it works for CSS files. You can create your own type providers, and it will give code hints while you're programming by processing that external source and exposing it as a type in your program. And there's a lot of other stuff that I obviously can't mention everything here, but it's a pretty cool language overall with a lot of interesting stuff. When people talk about functional programming, they can really talk about anything. There is no one definition that counts, and so it can be very confusing to think about it or to talk about it. What does it mean when you're doing functional programming? For me, practically, I find there's benefit in dividing it up into 3 levels. So level 1 is higher order functions, which means you can pass around functions through your program like you would pass around objects. You can take functions as parameters, or you can return functions from other functions. And this is, for me, if you're doing this, you're doing functional programming. This is easy to do in C# right now. We have lambdas, and so you can take this style and apply it to C# very easily. In fact, if you're using something like LINQ, you're probably using functional programming without really knowing that you're doing it. If you go one level up, you'll add to the mix immutability. So you try to work with immutable data structures, not with references. So you don't update references in place, but all values you use are immutable. This is really the sweet spot for F#. In F#, everything is immutable by default, while in C#, nothing is immutable by default. You can create immutable data structure in C#, but you have to jump through some hoops. You can create mutable data structures in F#, but you have to jump through some hoops. If you go one level up and add a restriction on side effects, which means a function can't write or read a database, for example, or a file, all a function does is take some input and transform it into some output or map it to some output. And this is really the essence of a mathematical function, or we call it a pure function. And this is a useful pattern for F#, but the type system won't restrict it. So you can't encode purity in the type system. This is something that does happen in a language like Haskell. So the sweet spot here would be more a language like Haskell instead of F#, but it's still a really useful pattern to apply to your F# code base, or maybe to parts of your code base. So in this talk, we'll really focus on level 1 and level 2. We'll start out with the basic constructs of F# programs, which will be functions and records to begin with. We'll ignore all the object-oriented capabilities because we're trying to focus on functional programming here. So if we want to write a function in F#, kind of look this. So we have an arithmetic module or class with an add function or method in C#, and then if we want to write the same thing in F#, we'll create a module and define an add function in there, and it will do exactly the same thing, but obviously syntactically it's different. So a few things to notice: there's no curly braces in F# here, they're not necessary. But what does matter in F# is the white space. So the indentation here is important, or the white space between parameters here. There's no return keyword in F#, while we do have that in C#. In F#, the last line is simply the thing being returned. So everything's an expression in F#. And the return type is added at the end in F#, while in C# it's added at the beginning. Now in F# we can also leave this out because there's type inference. So if I leave this out, it looks like this. Much more succinct, syntactically especially. Alright, if we want to apply a function, we can call it in C# and update the variable afterwards if you want. in C sharp, in F sharp, we would call it slightly differently. We would still call the function's name, but we add the parameters with white spacing between them, no brackets, no commas. And we define a variable in the same way that we would define a function, except the variable doesn't have parameters here. So we use the let keyword again, while obviously in C sharp that's a var keyword. And this result now is immutable by default. So we update a mutable value in F sharp with a left pointing arrow instead of the equal sign. But if we would try to do this, we would get a compile error because this variable is not mutable. Everything is immutable by default. If you want to make it mutable, we can, but we have to add a special keyword. So now we can update it in place. Immutable data structures are, bread and butter of functional programming, especially that second level. And so everything in F sharp is an immutable data structure by default. If we would want to do this style of functional programming in C sharp, we'd have to define data objects like this. So this is a person class, which has a name and an age, no setters, because again, we don't want to update it in place, we just want to create it and then not change it afterwards. That's what immutability means. So we have to create a constructor so we can actually create an instance of it. Notice that we'll always need to provide a name and an age. We cannot leave those out, they're not optional. We create a person as a whole. And then because we want value equality, we have to implement all this other stuff to get that with it. If we then would create two people, person 1 and person 2, and they're both named John Doe and they're both 27 years old, we assume them to be the same person. So if we compare them, they are equal, even though they're two different references. If you want to do the same thing in F sharp, that looks like this. So this is an F sharp record, this part here, and that's just creating a new type person which has a name and an age. And so we always create this with both fields like this, and we cannot leave any of them out. These records are immutable by default, and when we compare them, it's by values. So person 1 and person 2 are equal here as well. We don't have to do any gymnastics to get that semantic. So we use a equal sign here to compare. That's a slight difference from C sharp as well, especially the single equality operator. So there's no double equals in F sharp. Okay, so those were the most basic things you need to know, at least how to make records and functions. So I'll try to explain now the concept of higher order functions in C sharp first. So the most important thing to really remember is that functions are values. And that's, when functions are values, you can say the programming language as first class functions. You can pass them around then. So given a simple, object-oriented kind of data structure, a pet with a name and some behavior. So pet has a name and you can cuddle it and you give it some attention and it gives back some love. We can then create a pet, assign it to a variable. Now this pet variable contains data and behavior, it contains an object. If you want, we can also just assign data to a variable. But then if we can do that, if we can assign an object or we can assign just data, why can't we assign just behavior, just a function? And in fact we can. We have to explicitly in C sharp provide the type here, but we can. So we reference to the method itself here, or the function, but we're not calling it, we're not adding the brackets here. And so we're really assigning that to this variable. So this variable holds the function, not the return value of calling the function. That's a big distinction. So we can execute cuddle two ways now. We could call it directly on pet, so we say pet.cuddle, we give it some attention, get back some love, or we can use that variable to call the same thing. We call some behavior. Now, if you can do that, if functions are just values, that means you can pass them around. So if we have some pet consumer, we can pass it some data, a pet's name, or data and behavior in one object, the whole pet, or again, we can just pass the function. Notice we're not using those brackets here. We're not calling the function. If we would do that, we would execute it and then take whatever return value and pass it into this handle cuddle consumer. If you want to pass both data and behavior, kind of functional programming style, you could, for example, just pass them as separate parameters here. So we pass and the name and the method or the function. This means that functions can be a really handy tool for abstraction. I want to just demonstrate how that works in like a realistic code example. So this is some kind of pattern that I've seen in a few real code bases, where we want to get something from cache, and if it doesn't exist from cache, we'll go to the database, save it in the cache, and return the value. This is one that will get owners cached, but then you'll usually have like a whole list of these. For example, you can have one to get pets as well. So we have one to get our owners, one to get pets. These are almost identical. So we have the key here is different, and then obviously the types are different, and the database call is different. But otherwise, this is exactly the same code. So if we want to create an abstraction, what can we do? Well, a very easy way to abstract something is just to parameterize something. So we'll take the key, for example, and turn it into a parameter. Then both versions take a key and just use that key to look up something in the cache or to insert something in the cache. Now the only difference that's left is really, the function call here or the method call. I'll use them interchangeably. I prefer to think of them as functions at this point, because this will translate best to our F# code if we think of behavior as functions. And so we still have these differences, but otherwise they're actually exactly the same code. So this whole pattern of looking in the cache, checking if it exists, and then either returning it or saving it first, or going to the database, saving it, and then returning it. That's the same pattern. You don't want to have that 10 times in one of your classes. It's not necessary, especially if you want to change something about that. You'll have to change it everywhere, obviously. With functional programming, we can take this function and parameterize it as well. So that would look something like this then. We take the function as a parameter, and then we would call that function if we had to get something from the database. At this point, only the types are different, but we can then make them generic. This whole function doesn't care about what type it works on. It can work with any type. It's the same pattern. So if we want to then get our original versions back, where the key and the get are actually provided, we can create them like this. So if you want to get our original get owners cached, we can use our abstraction to provide owners and owners as a key and owners as a function to get them from the database. The same for pets. So we'll only have these differences here, but our core pattern is one generic function now. The next step is to call functions without names. Sometimes we've been referencing functions here by name, but you can also create functions anonymously. This is essentially what lambdas are. So if we create a mock version, we can use our same abstraction, but give it a mock function that just creates a new list in memory instead of actually going to the database. Well, we're creating this function here, but we might just be using it once. We're just using it here to create this mock data when we're calling it. So what we can do is we can take the implementation and just inline it here without assigning it a separate name first. That will look something like this. So this is the same function. We're just inlining it. We say, well, given when you call it, we'll execute this for you. But this whole thing won't execute until called. It's just the function without a name. Similarly, if we want to create a pet by ID, we can return functions as well. Or if you want to get a pet by ID, we can return the functions here. So create get pet by ID is kind of like almost a factory functions of functions. So given a string, it will give back a function that when called will go to the database to look up for that pet by ID. And so if you would call it, we could use the same get items cached and then call this function with the ID, and the result of this would be a new function that would actually be passing to the get items cached that would get called when it would go to the database. Obviously, we wanted the ID to be part of the key as well in that case. Again, we're just creating this here, this name to call it here, but if that's the only place we're calling it, we can inline it as well. So here ID is still in scope, so we can reference it directly here, and this part will create that function for us, or we're creating it inline, let's say, with the ID in scope. You actually know this already. If you use link, it's exactly the same thing. Let's say I want to get snuggles function that takes a list of pets and gives me all the pets that are that have the name snuggles. We call where, and then we give an anonymous function here. We can work in the opposite direction as well. If this is a pattern that we use a lot, we can give it a name and we can extract it and then reference it by name. So that would look something like this. So if this is our original version, we could take that and we say, well, we have a function here that is snuggles that will take any pet and it will determine whether it's snuggles or not and return our boolean, and then we can just pass that function here directly. Look again, no brackets here, so we're not actually calling it, we're just giving it a function that the where will call itself whenever we're evaluating our enumerable or our list. Notice now that you know this, something you might be doing is, let's say you do some select to transform a list of database objects to a kind of a DTO. You might be saying, well, given an X, call this function with that X. Well, you're creating a new function here, but all that it does is call another function with the same value. So this is actually completely equivalent to just passing in the function. So whenever you're doing this, consider maybe just passing in the function itself. Alright, this was a lot of C#, and you'll probably be wondering, well, wasn't this talk about F#? So let's try to take that cache function we just saw and turn it into F#. But right before that, I'll have to show you one more slide with C# code. Because since we parameterized our values, we have to take into account that they can be null. So we'll have to add some checks, some null checks, and then show an argument null exception if they are null. And this is the code that we will then convert to F#. So let's get started. We start with defining our function, and we'll pass here the key and dbGet. I won't be adding the type annotations, but obviously if you want, you can. Then I'll get the cached items by calling get by key key. Notice I'm not showing these null pointer exceptions here, not checking for null, because in F# nothing can be null. Nulls are just not a thing in F#. The compiler will prevent you from doing that. Every value has to be a value. It can't be something else. It can't be null. If you define a function like this, the compiler will only allow you to call it with things that are actual key and actual db get. Nulls just don't exist. So I don't have to do those checks. I can leave them out. I don't have to unit test it either. The compiler, the type system, will take care of that. So that means that I can get my items, but in our C# version, cached items might be null, because then if it's null, we know it doesn't exist in the database or in the cache. I'm sorry. So how do we do this in F# then if we don't have nulls? Well, to do that, we have to take a little detour and talk about discriminated unions. So we've seen what a record is. A record is, a new type that is a combination of other things. So a pet is and a name and an age. A discriminated union is mutually exclusive. So where a record says, well, a pet is and a name and an age, this discriminated union, current user, says it is or anonymous or an authenticated user. And in the case of anonymous, there's no data attached to it. But if it's an authenticated user, there's some data attached to it, which would be a GUID. So this is kind of thinking like it's an enum where the cases can have data attached to them. But it doesn't have to be data, and depending on case, it can differ. So record is and this and that. Discriminated union is or this or that. So to give a quick example of this, if I want to create this user object, like let's say the current user, I could say, well, I'll create an authenticated user and then I'll pass it in a GUID. I'm adding brackets here because I want to evaluate new GUID first and then have the result passed to this function. So brackets are in generally optional, but sometimes you do need them to say which you want to execute first. If I wanted to create the current user anonymous, I could just use the anonymous. So these things are called data constructors. If I have a current user object, I can do something with it, but first I have to check on it. So I have to pattern match. This is called a pattern match. So I say, well, if a user is anonymous, I'll do this thing. And if a user is an authenticated user, of which the GUID is this thing, I'll do this other thing. So I can take a GUID here and do something with it. So those are, functions, immutable data structures, of which we have records and discriminate unions, together with the strings and ints and everything like that, is really the minimal group of concepts that you need to write complex programs. That's really it. There's, you can go into a lot more, crazy stuff, let's say. But this is really the basics that you need. A pattern match especially is really powerful. I don't have time to go into it in the rest of this talk. But it is extremely powerful. So if we want to create another type to say, well, we can't say, there's no nulls, but we do want to know whether something has a value or not, or represent that. Then we can create our own discriminate union, which takes a generic in this case. I'll call it option. And it will say, well, either we have some value or we have no value. And I am creating this type here and showing you the definition, but this is already baked into the language. Which means or something has a value or something has no value. So the none case here is the same as a null. And you can create, optional pets here by saying, well, I'll say this optional pet is none, which is the same as saying null. Or there is some pet, and then you have to, construct it with an actual pet. We can pattern match on it. So wherein, if you had some kind of optional pet in C#, the pattern kind of looks like this. So you might have noticed, some things in C# APIs returning like a has value property, and you can check on that. So if you check on the has value and it's true, then you can access it by value. And other case, there's nothing. Something like that, exists in F# with this option discriminate union, where you can pattern match and say, well, if there's some pet, I can do something and I can use this variable to actually reference to the pet itself, right? So optional pet here is a type optional pet, and a pet here is a type pet. Or in the none case, I can do something else. So our key here and our db get are parameters, and we'll use the key to go look in our cache for something. Cache get by key will return an optional. So cached items is gonna be an optional of something, which will be generic. So let's say an option of t here. And we can pattern match on it and say, well, if we have some items, just return those items. We kind of extract the items from the optional and return those. Now at this point, the compiler will tell us, well, there's an incomplete pattern match. We have checked on the some case, but there's another case, there's a none case. What if there's no value? And we still have to check that. So that will give you a warning, and you should usually treat this warning as errors. This is a really powerful thing that's in the language. It really helps you create software with less bugs, because it will tell you when you're missing something or forgetting something. So in the none case, we color db get, we do the save to cache, and we return the items. And this is our same implementation as in C#, but we just convert it to F#. These are really the only building blocks that you need: passing around functions, records, discriminated unions. If you know this, you can get started running your own programs. So if you want to create again our get people cached and get pets cached, we can do it in a very similar way again. We pass in a string and our db function, and it works exactly the same as in our C# code. Underneath here, we're using an anonymous function. The syntax is fairly similar in C#. In C# you have a fat arrow and you don't have this fun keyword. In F# there's the fun keyword for a function, but here we're just defining an anonymous function. Alright, we're coming to the end of the talk, but before that I want to explain a little bit more about why immutability matters to me. I first experienced it when I wrote my first code in F# and been working on F# program for a while, and then went back to a C# program where I had to find a bug. So I had to look at C# code that someone else wrote, and the C# code was using mutable data structures and update in place, and it was super hard to follow for me coming back from F#. There are really clear advantages of immutability when it comes to parallelism, because you can do things without locks, etc. But there are also advantages in synchronous code, just in reasoning about code and seeing where things change. But I've not really seen an explanation or found an explanation that really demonstrates that in a simple way. So I'll try to show that here. I'm not sure if I'm going to succeed, so please let me know what you think afterwards. But I'll show you some demo code that hopefully will demonstrate the issue. So let's say there is a function in our program that registers a pet. So we'll get a pet from our cache, and we'll have to somehow pre-register a pet, maybe to an external system. Then we can assign an owner to a pet, and then we create like the final registration, which we then return. We don't need to care about implementations here too much, but let's notice a few things. If this is multi-threaded code, which it very likely will be in let's say, Web API, there's a glaring issue already in this C# mutable code. Since we're getting a pet from cache, it's still referenced in the cache, which means that when we're passing it to this pre-registration here, and then afterwards to this assign owner, another thread could have changed something in the pet reference. So we might be registering with a pet that afterwards we're trying to assign an owner to, but it will have changed in between, which can cause for subtle bugs. Maybe they're rare, maybe they don't happen a lot in a lot of like business sign applications, but when they happen, they're really hard to track down and find. You have to be really careful with this stuff. So you have to start adding locks, etc. And this is really where immutable data shines. If pet can't change because it's immutable, then we just don't have to worry about the problem. So this is the easy case to make for immutability, and why it's really nice to have also as a default. But there are more issues here if you look at it even from like a synchronous perspective. Let's say I find that given an ID to my register pet, I get a registration back, but there's obviously a bug in there somewhere. Like the registration is not entirely how I expected it to be or how it should be. There's a bug in there. There's a mistake. One of the fields is off or whatever. What I have to do here, let's say I have this bug. I say, okay, I have to walk backwards basically. So I have my registration and like one of the fields is wrong. So I'll have to go dive into this create registration function because that's where the registration is coming from. And maybe when I dive in there, I see, well, this registration, let's say pet name, is coming directly from pet. And that's where the bug is. So now, okay, so I have to trace it through pet. So where is pet referenced here? Well, pet's reference to owner, or to assign owner it's given, and to pre-register pet, and here it's gotten from the cache. Which means I'll have to dive into both these implementations because both of them can change pet. Where is pet's name coming from? Because that's like the next step, right? Where is it going wrong? Well, if assign owner is changing a pet, it could change its name, so I have to go look in there to see where is its name changed. The same with pre-register pet. So there's no logical way here to kind of see, well, where is the name changed? I really have to almost look at my whole program, see where is name changed or pet name changed. I can't just like walk through the code. While the opposite, when this would be immutable, I know that pet can't be changed inside these functions, in these implementations, because it's immutable. So I know that it's coming out of the cache wrong already. And now this gives us to the next step. Well, where does it get inserted into the cache, right? And now cache is kind of like a global mutable store as well. So you actually have, the same problem. Suddenly you have to go look at the whole program. But even then, when you have to go look at the whole program, you just have to look at where pet is inserted into the cache and then take it from there. While if pet was a reference mutable object, it doesn't even matter where it was inserted in the cache. It can be changed everywhere. So even in presence of some mutability, having the immutability by default is still helping you reason about the code a lot. So when I was doing this in F#, I really got used to like, okay, following pet, from here to here, skipping all this code in between, and then so getting back to C#, that was a really almost shocking experience for me. Especially when the implementations of these things can be huge, and maybe there's a lot of more steps in between, or a lot more parameters going around, and it can be really tricky for some bugs to find the problem. So if I go to F#, and this is exactly the same thing, so it's syntactically different, but everything is immutable. So here I know if I follow registration, the bug in registration to create registration, as it's coming from pet, I can trace it right down to here, skipping all these steps. So that's hopefully a small example of how this immutability is not only really useful in light of parallelism, but can also help with reasoning. And if you take it a step further, to that pure functions, Haskell-like world, you have even more benefits in that, that lay in the same vein. So that's really all I have time for. There's a lot more out there to explore. So I just want to point you in the right direction. If you have questions or you want to do something specific in F#, you can always send me a tweet or an email, and I will try to point you in the right direction. If you want to write functional first web apps, you should really check out the Safe Stack. It uses a Fable compiler to compile part of your code to JavaScript, so you can write a web app that way. And there's a RPC mechanism that lets you share types between the backend and the front end. I think it's the most pleasurable experience I've had writing web apps ever. If you want to study a little bit more, learn a little bit more, there's 2 blogs here that I really recommend that are also geared towards C# developers and will really take your hand and teach you all kinds of different stuff in F#. If you're really into data science, you should check out this last page, and it will set you up for your data science environment and experience. That's the end. I still have time for questions. My name is Janne Siera. You can follow me on Twitter if you like, or check my blog. I've started recently putting some blogs up. And like I said, if you have any questions, either tweet me or email me. I'll try to help you. If you would like some training, or your company would like some training with F#, I can definitely help you with that as well. I'm a freelancer and a consultant, and I love doing this stuff, so please contact me. Thank you very much.